affiliated and unrelated. So this is all WashU is affiliated and not Boeing related. So the talk is about weak measurements and how they can reconcile incompatible observables. And so the outline of the talk is basically going to be to break down that title. We'll start off with weak measurements, describing what weak measurements are by sort of describing quantum measurements in general. And then I'll talk about a little bit of incompatible observables as quantified by uncertainty relations. And then finally, we'll get into the experiment where I describe the reconciliation that can be done with these weak measurements. Okay, so off to the first part of quantum measurements. So quantum measurement is sort of the simplest process, or the simplest process of a quantum measurement is measuring the spin of a spin 1/2 particle. This is a nice simple example because there are only two outcomes, up or down. And the measurement process is somewhat straightforward. You might picture sending these spins through a Stern-Gerlach apparatus and measuring the projection of those spins onto this screen in the back. We know that this corresponds to measuring the sigma z component of the spin. We'll define that as sigma z. And of course, if we look at the screen, then we get sort of two blobs, one corresponding to spin down, one corresponding to spin up. And this is pretty old physics. This is the chapter 1 of most quantum textbooks. And so yeah, these are expectation values. Now, the perhaps surprising feature of quantum mechanics that we all know and love is that when I send a sort of left-pointing spin through this Stern-Gerlach apparatus, I don't get a blob that's in the center of the screen, but actually I get a distribution that matches the sigma z plus and -1 distributions. And one of the spooky parts of quantum mechanics is that this x measurement, which we know is, of course, preparing a sigma x eigenstate, and the z measurement of that x eigenstate is a completely random process. There's no way to show whether one particular spin will land on the top side of the screen or the bottom side of the screen. And so the sort of question, and sorry, this randomness is due to the incompatibility between sigma z and sigma x, namely the fact that these two operators don't commute. And so the main question that I'd like to ask in this talk is how we might mitigate that kind of measurement incompatibility. So is there something that we can do where we send in this x state and get a sort of less random outcome for the z measure? And of course, there's some, I forget what the name of the rule is, but there's a rule that if you ever ask a question in a talk, the answer is always yes. And if you ever ask a question in a title of a paper, the answer is no. So this is a talk, and so the answer is yes. Anyway. Okay, so how do quantum measurements work sort of in practice? And sort of the hard question about this is how we lay our grubby classical hands all over delicate quantum states. So of course, it's not enough to wear gloves like pictured here, or put these systems into dilution refrigerators like you see in the back here. But a real sort of quantum measurement always involves some kind of pointer. So our delicate quantum system here over on the left interacts with some pointer system. And that pointer system can then be, in a sense, classically measured, where the classical measurement is projective and destructive. In the experiments that I'll tell you about, the qubit is this little black square in the middle. It's a transmon superconducting circuit, and so there's a little patch of aluminum right here. And then the pointer is this cavity state, this hole in this block of aluminum. And that, again, realizes the pointer, the photons in that cavity interact with the qubit and allow us to measure the state of the qubit. Okay, so let's, so I guess I want to go back to this Stern-Gerlach example and show how the, what's so impressive about this experiment is that it couples some quantum degree of freedom, the spin of an electron, or spin of a silver atom, I guess. It couples that degree of freedom into a different degree of freedom, namely the position along the screen. And so in this sort of simple example, this old example, the pointer, so to speak, is the position along this screen, and that position degree of freedom couples to the spin degree of freedom from the quantum system. So that's the kind of intermediate process by which this quantum measurement happens. The spin looks like position. And in this case, the because in order to get these blobs, so to speak, to be well separated, that is the noise on our measurement, or excuse me, the noise on our estimate of the state, to be much better than the variation of that. We use a long chamber. The Stern-Gerlach apparatus has a long distance, and that gave us a high quality projective measurement. In certain circumstances, it's useful to have partial or weak measurements, where we effectively take the Stern-Gerlach apparatus and we just chop it in half. So now the two distributions for spin being up or down are a little bit more mixed, and so we don't have complete information about the system. But the benefit is that when we send this X eigenstate through, we also don't get complete information, and therefore we don't fully project the wave function onto one of the sigma z eigenstates. So this brings up another sort of aspect of these uncertainty relations, and that is that there's disturbance that happens as we measure a state. This plus X state was projected into one of plus or minus X, plus or minus Z. And if we do this weak measurement where this Stern-Gerlach apparatus is shortened, we don't fully collapse the wave function. And in a sense, excuse me, we can see what's happening while we measure the quantum system, while we measure the spin. And so this disturbance uncertainty will be an important part of the uncertainty relation that I'll tell you about. Okay, and just to describe the experiment a little bit more, the physical readout process involves, again, these blocks which contain photons. The photons are in this coherent state, which means that in the I and Q quadrature representation, they again have these kind of these blobs. We initialize this blob to have what we define as zero phase. And then upon interaction with the qubit, whether that blob shifts in phase, either going left or right, depending on whether the qubit is in the ground or the excited state. And just like for the Stern-Gerlach experiment, when these two blobs are well separated, that corresponds to a projective measurement that collapses the wave function and gives us precise information about the qubit. In this circuit QED platform, we have a straightforward knob to turn where we can decrease the amplitude of that coherent state. And in that case, the two blobs for qubit, the qubit state being ground or excited, results in a partial measurement. And so we get the same kind of overlap, incomplete measurement, incomplete projection of wave function. And so with this kind of weak measurement, we get a new tool by which to measure these systems. So let me walk you through what that kind of measurement process looks like. So if we take a histogram of all of the I components of this these photons, we might get a single Gaussian that looks something like this. And if we, excuse me, imagine that we start off in this plus X state, and then we measure some small outcome J, oops, up here. And upon measuring that J, we know that the qubit state is now a little bit closer to the excited state. So we then update our state of knowledge. This state moves slightly. And so we have a new state upon measurement. So we can continue this process, getting, excuse me, maybe more positive values. That causes more back action, maybe slightly negative values, more sort of negative back action. And we can do this process continuously, as well as we, as fast as we can track the measurement outcomes, we can update states continuously. That measurement update process follows these POVMs under continuous distribution. And you can see that the Krauss operator here, this M sub J for an outcome J, is essentially a Gaussian weight of projectors. So there's this Gaussian prefactor and then a projector onto the various photon states I. And through this excuse me, measure and update process, we can track continuously these quantum trajectories. Now, in this work, excuse me. In this work, we'll just focus on single measurements. So we kind of integrate for a long period and update just a single point after measurement. Okay. And again, the fact that our measurement is not fully projective tells us that we're only imparting partial back action, in a sense, at the cost of only getting partial information about the state. Okay. So now let's go to the kind of second part of the talk and describe the uncertainty relations of these weak measurements. So we're all familiar with these kind of uncertainty relations that come from commutators, where the product of variances, I guess this is standard deviations between two operators A and B, excuse me, is lower bounded by the failure of those two operators to commute. And sort of in the case that we'll be focusing on, these two operators will be sigma z and sigma x. Now, this uncertainty relation is valid and true, but it's actually not very helpful for the case that we're going to consider. It's not helpful for a few reasons. First of all, if we work in states that are in the xz plane of the Bloch sphere, this bound is always 0, because the expectation value of sigma y in the xz plane is 0. And so again, this statement is true that the variances will always be positive, but it's not a very useful statement because we already knew that based on the properties of just of variances alone. But actually the story gets a little worse. And that's sort of an issue with the standard deviations themselves. Let me illustrate those problems with a simple example. And in this example, we're going to consider a spin 1 system. So there are 3 different outcomes. And imagine that when we come on the scene, the state is equally, excuse me, equally distributed between all 3. It's in a mixed state. And there's a one-third chance of observing each spin output, +1, -1, 0. The standard deviation in this case is the square root of 2/3. And so that'll be our kind of base case. Now, imagine that we perform a measurement that excludes one possibility here. So here we're saying that, for example, the 0 spin is not allowed. We've gained information in that we know that it's not in this state. And so there's a higher probability that it's in either plus or -1 state. And yet, if you go through the variance calculation, the variance has actually increased despite our learning information. And furthermore, this story changes if you exclude a different measurement. If our measurement excludes the +1 case, then in that scenario, our uncertainty does decrease as expected. And so it turns out that excuse me, this result comes from the fact that the standard deviation depends on the fact that there's a kind of scale to the problem. The variance that because the variance depends on the x coordinate, it inherits any of the scale that goes into the system. And so in our case, in the case of the spin 1 system, the fact that we're using ±1 or 0 introduced scale problems that cause this uncertainty relation to fail. Anyway, so because of those reasons and a few others, we're going to move away from variances, and we're going to use entropy instead. So entropy is a similar kind of expression. It's the average value of this log 1/p quantity. This log 1/p is often called the surprisal of a probability distribution. And it's related to, or it's supposed to quantify how much information you gain from a measurement outcome. And so this entropy is, so this is just the Shannon entropy of a probability distribution. And that Shannon entropy is beneficial because it has these nice properties that when the probability is higher, when an event is more likely, that information conveys less information about the process. If you expect something to happen 95% of the time, then there's not much information gained from that highly likely event happening. And entropy is also beneficial because if you have a two-dimensional probability distribution, like we'll have in a moment, the independence of those probabilities causes the entropy to add together. And then also entropy connects to various other fields like thermodynamics and cryptography, and it makes really interesting connections to those other fields. So for the rest of the talk, I won't talk about variance-based uncertainty relations, but instead I'll talk about entropic uncertainty relations. Oops. And in particular, the sort of classic entropic uncertainty relation that we'll deal with has this kind of form, where the product of variances from up above now is the sum of entropies. And it's a sum because it involves logs and sort of those sorts of things. And then the overlap, the bound, has this overlap term, which calculates in some sense the distance between eigenvectors of the two measurement operators, A tilde, B tilde. And so we'll choose A and B so that the overlap is maximized. And again, this H is just the Shannon entropy of the probability distribution of measured outcomes. Okay, so that's the uncertainty relation that we'll sort of base all the work on. And so let me tell you a little bit more about this uncertainty relation. So in the case of the Stern-Gerlach spin measurement that I mentioned at the beginning, we're going to consider measurement incompatibility between sigma z and some operator sigma theta, where theta is an angle in the xz plane domain. So this was the picture that we started with, where we have a, say, spin up particle that we're sending through. And so remember that in the case when we sent spin up through this particular Stern-Gerlach, the measurement outcomes were not surprising. At 100% of the time, the spin was projected onto one of the sigma z eigenstates. And so these measurements are not uncertain. And we'll always sort of consider this case. And so this initial term should go to 0. We also considered sending this kind of plus x state through the Stern-Gerlach. And I'll just note that that's equivalent to sending the same spin up through a kind of sideways pointing Stern-Gerlach. And so in between this sort of upward oriented and sideways oriented Stern-Gerlachs, there's a full parameterized measurement that we can perform, measuring at any angle theta between z and x. And so that'll be the sort of Pauli operator that we measure is a linear combination of sigma z and sigma x. Okay, so in this case, the overlap is fairly straightforward. It's just a cosine or a sine squared. And the cosine or the sine depends on whether your theta is above 90 degrees or less than 90 degrees. Okay, so this is the sort of basic uncertainty relation that I'll talk about for the remainder. Let's take a look at what the uncertainty of this kind of distribution looks like. So here I'm plotting the left hand, the entropy, the total entropy, both the initial term, which we expect to be 0, and the second term as a function of this measurement angle theta. So here, when theta equals 0 or when theta equals pi, the uncertainty is minimal. Again, because we're preparing sigma z, we're preparing a z eigenstate, and we're measuring sigma z, and so there's no uncertainty in that outcome. And that's represented as the 0 bits of entropy. Then when we move over here to theta equals pi over 2, we've again prepared sigma z, but we're measuring sigma x, and so these outcomes are maximally uncertain. The entropy maximizes at 1 bit, and this 1 bit corresponds to a 50-50 distribution, sort of a single coin flip, being having equal chance of landing on heads and tails, and that probability, the 50-50 distribution, is in a sense the definition of the 1 bit. So we get 1 bit of uncertainty maxima and 0 minima, 0 bits. Okay. So that's the kind of left-hand side of this equation. Let's take a look at the right-hand side as well. And so you can see that the bound here is relatively tight at the cases that we discussed at pi/2, 0, and pi. But then there's this kind of gap here in between. And it's kind of an open question in this community about how good of an uncertainty relation one can derive theoretically. And so this, this is kind of a basic uncertainty relation. And so the tightness isn't great, but it's a good working example. Okay, so now let me get into this sort of core measurement of the top, where now we're going to introduce a weak measurement into this uncertainty relation. And remember that we're asking, what is the advantage that we can get in terms of lowering the uncertainty, lowering the randomness of the outcomes by introducing these kind of weak measurements. So again, we'll consider the sigma z measurement, which we expect to be 0. And now we have a sort of joint measurement where A is some again, poly observable that's measured weakly. And then we have another theta f measurement, again, in the xz plane of a box sphere. And we'll sort of do these 2 measurements back to back. So weakly measure and then strongly measure. And then we'll talk about the bound. Okay, so again, we have these 2 angles, theta A, theta f, corresponding to the weak measurement, sort of a little bit more opaque out here. And then the projective measurement and angle theta f. Okay.
Just a quick clarification. So you're imagining first you have weak measurement represented by you're measuring along the theta A basis, and you have then a final strong measurement at the theta F basis.
Exactly.
Okay, thank you.
And this is the entropy of the joint probability distribution of those two.
That's right. Yeah. So it's the 2-dimensional probability. But okay, I'll make a comment about that in a moment. But so actually, what I'm plotting here is the joint entropy minus the weak measurement. But so this is the measurement of this uncertainty term as a function of this strong measurement angle for a fixed weak measurement angle. And so we see, again, qualitatively similar features where closer to 0 and closer to pi, we get minima. Note that the minima has shifted slightly. But the most important result, the most important result is right here in the middle, where theta f is equal to pi/2. And so we've, again, prepared sigma z, but measuring sigma x. And with this particular weak measurement configuration, we see that the uncertainty has actually decreased relative to the case where there is no uncertainty, where there is no weak measurement. So in the presence of the weak measurement, we get something like 0.2 bits of less uncertainty when we measure a sigma x eigenstate. Measure sigma z of a sigma x eigenstate. And again, I'll note that I've subtracted off the uncertainty associated with the weak measurement because it adds essentially extra information due to the kind of high resolution of the measurement. Okay, so this so I want to explore this result a little bit more, and so let's zoom in on this pi/2 case. Oh, sorry. Before I do that, yeah, I want to highlight again that this weak measurement, the fact that these 2 measurements are back to back, is a direct study of this kind of disturbance feature of these uncertainty relations. And so, in essence, what we've done is weakly measured with 1 Stern-Gerlach, and then strongly measured with a longer Stern-Gerlach. And this sort of combined measurement allows us to get a picture of what's happening in the interim while we're measuring. Okay. And so this, so I mentioned that we fixed the theta A measurement axis in the previous plot. So here's the distribution of entropies that we measure for both the theta A and the theta F coordinates. So what I showed you before was just a slice of this graph. Now, again, we see kind of reasonable minima here when either theta is 0 or pi, so all in those four corners. And then red maxima occur when either measurement is closer to pi/2, reflecting the kind of intuition that we have about incompatible observables, sigma z and sigma x. Right. Now, what's surprising about this is that the minimum, so let me focus on a kind of horizontal slice. What's surprising is that when theta f is pi/2, namely, again, we prepared z, measuring x, the minima does not occur at, say, theta a equals pi/2, that you might expect, but it actually is closer to pi/4. So when we started this project, we were thinking, if I handed you a spin up state and asked you to measure sigma x, and then try to guess the outcome, your initial guess would be kind of hopeless. You'd have a 50% chance of getting it right. But then if I tell you that you're allowed to weakly measure that system before you do your x measurement, you might think about what the optimal measurement axis that you would make for your weak measurements. When we started off, we expected that you should just weakly measure the same observable that you'd like to predict. And so weakly measure sigma x, that gives you a little bit of information to better predict the next outcome. But it turns out that measuring not sigma x, but sort of a linear combination of sigma z and sigma x leads to the optimal decrease in the uncertainty. Let's look at that a little bit more in detail. So here, I'm going to show you the entropy, the relative entropy of this full uncertainty relation with the initial entropy, both of the weakly measured z and the weakly measured x. And so that's analysis subtracting off this kind of baseline entropy at this point here. And so we're going to look at this horizontal sweep along the axis. Okay, so in this case, we see that the minima here, of course, like I said, occurs at pi/4 and not at pi/2. In fact, sort of ignoring the experimental non-idealities, it turns out that the pi/2 case is exactly the same as if you is exactly the same as the x measurement. And so there's no advantage to sort of pre-measuring this quantum state. Now this sort of entropy measurement is just one of the tools that we have in our tool belt. One of the other cases that we can do is called full process tomography. And if we do that, we can sort of recreate this in a kind of cartoonish way the effect of these measurements. So when we measure this block sphere state updates, and it has some small amount of back action towards the measurement eigenstates. And so in this case, when we're measuring theta a equals pi/4, the state moves sort of slightly towards that eigenstate. So you can represent that as a rotation on this block sphere. The state rotates, but it also shrinks. It also is subject to measurement-induced dephasing and inefficient detection. It turns out that dephasing is one of the key drivers of this physics. That the reconciliation of this z eigenstate to the x eigenstate is not only due to the sort of back action of the measurement process itself, but the dephasing that happens under the course of measurement. And so it's those two physical drivers that lead to the disturbance uncertainty, both the sort of unitary update and the dephasing. Okay, and so let me take a quick aside to discuss some interesting properties about this entropy, and maybe get to some kind of surprising results about this. So I just told you about how we've shown how you can decrease the entropy by doing these weak measurements. And I told you that the entropy is this kind of Shannon entropy at p log p. Turns out this entropy is just one part of a broader entropy family. And those are all, this is the so-called Renyi entropy, which is parameterized by some number alpha. And in the case that, in the limiting case that alpha goes to 1, this Rennie entropy converges to the Shannon entropy. Now, the Rennie entropy has this prefactor and is related to the log of the magnitude of the probability vector. So this says you have lots of different outcomes for your probability distribution. If you treat those outcomes as a vector, in however many dimensions you need, and you take the alpha norm of that, that vector, the log of that vector norm gives you a kind of entropy. And so what we're saying by decreasing entropy is that we've effectively shortened these block vectors. And so we can think of this weak measurement process as effectively cutting out sections of the block sphere, shrinking part of the coordinates of the block sphere. So that's just an interesting aside about how entropies, these information theoretic properties, are also related to kind of distances in this probability space. Okay, so I've been focusing pretty extensively on the left-hand side of this inequality, the entropies here. Now let's take a look at the right-hand side. So I've been presenting this as this kind of innocuous F weak value, only because the full expression is a little bit hairy. But we can break it down by looking at it sort of term by term. So this first term, log of a kind of overlap, is very similar to what we had in the sort of simple entropic uncertainty relation that I talked about a while ago. And so this term turns out to be related to the sort of weakness of the weak measurement. If you take a Taylor expansion of the weak measurement operator in the weakness of the drive, there's part of it that's proportional to the identity that does nothing, and part of it that is proportional to the operator that you're trying to measure. And this first term is the identity component of it. And so this essentially has no back action and is essentially no different from the original entropic uncertainty relation. The more interesting physics comes from this second term, which involves some normalization quantities that relate to the measurement process, the technical details of how that process works. But more surprisingly, it comes up with this weak value, WIF. And so this sort of whole expression should really just be translated into having a negative proportionality to the weak value. And so this is really interesting because weak values have, as we're very familiar, have excited a bit of controversy about how what they mean, when they're relevant. And so this entropic uncertainty relation calculation provides a direct case when these weak values show up. The weak values provide an update to the bounds of uncertainty relations. Okay, so let me tell you a little bit about weak values. So these weak values are quantities that have some kind of surprising features. It's excuse me, supposed to be some kind of expectation value, but given the denominator here, it turns out to result in measurements that go far outside the spectrum of a typical value. So as we know, if you measure a spin 1/2, the sigma z measurement should range between +1 and -1. And in many cases, you can get measurements far beyond that. And Jordan Dressel came up with a nice, really clean explanation that I really liked. So I wanted to share that with you. That if you consider the measurement process, this having a unitary measurement update between some initial state and a final state, that measurement can be Taylor expanded and simplified. And you can see that the ratio, excuse me, the weak value relates to this ratio of probabilities. The probability, how the probability has shifted slightly under the sort of unitary effect of measurement. And so let me describe the sort of the experimental way that we do that. So we have this expectation value, and if I think through what this expression means, I will need to start with some initial state I, weakly measure whatever variable A, whatever operator A. then projectively measure into some final state f. But as an experimentalist, as I have a lot of leeway about what I and f correspond to, which eigenstate they are, which operator they correspond to. And so I can choose, in one case, for I and f to be equal. In this case, I am initializing in some state, weakly measuring some different angle, some different component of that spin, and then projectively measuring and post-selecting on the cases where I ended up in the same spin state. In this case, the data looks fairly well behaved. When theta is 0, I get +1 corresponding to the sigma z coordinate starting in 1, ending in 1. And if I go down to 180 degrees, this is effectively measuring minus sigma z. And so I get a sort of -1 outcome, and it comes back up to 1. The strange things happen when I start to post-select into nearly orthogonal final states. So this scenario corresponds to starting in the ground state, weakly measuring at some angle, and then discovering after that measurement that I've ended in the excited state. So in this case, especially in certain measurement, weak measurement configurations, when theta A is close to pi/2, the sort of average value of this weak value has to be beyond the normal ±1 spectrum. In the experiment, we observe weak values as high as like 2.5, 2.5. And so these anomalous weak values are exactly part of the reconciliation that happens in these uncertainty relations. Let me go back to them. And so again, I told you in the first half of the talk with the left-hand side, how these uncertainties related. And now I've shown you how the weak values are integral to the bound of that uncertainty. So by getting these strong values for the weak value, these high anomalous values for the weak value, that effectively brings the bound down and allows these two incompatible observables to agree more. And so, experimentally, we measure the entropy as a function of these two measurement angles. We can also measure the bound as a function of those two measurement angles. And the values here, roughly 5 bits, are of course always greater than the bound, of roughly 2 bits. And you can see that the sort of average tightness that we see between the measurement and the bound is something like 3 bits. So it's not ideal. And that non-ideality is due in most part to the inefficiency of the detectors. But nonetheless, we have sort of the consistent results between both the entropy and the bound. Namely, this sort of snaking of the maximum of the bound, again, is directly related to the weak value here. The fact that the weak value at this pi/2 kind of value, the fact that that is anomalous tends to shift the distribution, shift the bound, and allows these operators to agree more. Yeah. So in conclusion, I've shown you how by adding this weak measurement in between two strong measurements, you can effectively reconcile two incompatible observables, decreasing entropy, and being able to better predict what the measurement outcomes will be. And of course, I'm the one presenting, but this is work due to an entire group. So I'd like to thank my PhD advisor, Katie Murch, and Teo, who did a lot of the initial work, and our theory collaborator, Nicole. Well, thank you for your attention, and I'm happy to take questions.
Thank you, Jonathan. Let's start with questions from the room. Matt.
So I didn't quite buy the argument for not using standard deviations and variances for it. So there were two parts to it. One is you can have a situation where you learn something and end up with a sort of with the higher standard deviation.
Mhm.
That can happen to entropy too, right? So, for instance, the classic example of that is suppose that I really think that my car keys are in my pocket. But if they're not in my pocket, I have absolutely no idea where they are, right? They could be under the sofa, under the bed, blah, blah, blah. So if I reach into my pocket and find that my car keys aren't there, then my entropy radically goes up. So that can happen to all uncertainty measures.
Okay.
It's the average, however, that goes down, right? You look at the average uncertainty. And I think that might happen with the standard deviation as well, I'm not sure. But the other thing is with the scaling, which matters when you have outcomes that if you have multiple if you have like 3 or more outcomes, it matters. But here we're talking about spin observables which have values of +1 and -1. Right? So you have a fixed scale for everything. There's only 2 outcomes, so I don't really see how that scaling can play a role. And in that light, I wonder whether you could look at the same kind of phenomena you're talking about with uncertainty relations for variances and standard deviations that are based on the sum, because some of those exist in the literature. So I was wondering whether it would be interesting to look at standard deviation based on uncertainty relations as a complement to this to see if similar things happen.
Yeah, it's a good idea to explore all of the possibilities, all of the uncertainty representations, both variance and uncertainty and entropy. And I'll say that this work was connected to kind of cryptography applications, and so those are often based on entropy.
So have you looked at the min and max entropy in this context then? Is there something else?
Yeah, I haven't looked at it very significantly because the distribution, the min-max entropy sort of ignores the details of the distribution. It just takes how many outcomes there are, or that's the max entropy, and the min entropy is something else.
So the log of the max.
Yeah. And so the if you look at the probability distributions underlying these measurements, the qualitative shifts, the qualitative changes is that the means sort of shift very slightly. And so it's really the subtlety of the probability distribution that makes these uncertainty relations.
Other questions in-house? Oh, it's Athaga, you have a question.
Yeah, I have a question related to the.
Speak up so they can hear you on the.
Yeah, I have a question related to the relation. I was just wondering whether the entropy based uncertainty relations and the Heisenberg uncertainty relation are they related? Like, does one lead to another always, or
I'd say they're pretty different, just because one is based on sort of the evaluating a commutator between them, and the entropic uncertainty relation is qualitatively different in that it doesn't depend on any states, and so so it has these very significantly different features, and so certainly mathematically I don't think you can get from one to the other. And they also have this just different feature of either being state dependent or not being state dependent. And that's another sort of interesting part of this uncertainty relation.
Okay, are there any questions from the Zoom audience? Okay, hearing none, I'll ask one. So you showed us these plots of your results about this inequality, and you showed that the inequality was satisfied, but you pointed out there were like 3 bits of separation, and you blame that on detector inefficiency. But I'm wondering if suppose you had perfect detection efficiency, how close do these left-hand side and the right-hand side get to each other at this inequality?
Yeah, it's a good question. So if you evaluate all the expressions theoretically, you get something like half of a bit. And the 2.5 bits remaining is consistent with the sort of spread in the width of the distribution that we'd expect from that. quantum efficiency.
All right, if you didn't do any weak measurements, whatever, you showed us these plots at the beginning between the entropic, and you had this curve, and you had the cusp-like behavior, right? What's the gap there in that example?
In that example, the tightness is pretty good in the middle at the regions where they touch.
Yeah, right.
Yeah, so it's tightness is 0 here at pi/2 and 0 in pi.
Yeah,
And
but it looks like about half as well away from that.
yeah, that's a good point. So the so this distribute. So of course the tightness depends on the measurements that you're doing.
Yeah.
It's tight out here now. But it turns out that in the other case, in this two-dimensional case, the weak measurement case, it's sort of a full half bit.
Have binary results, plus or minus 1.
Mhm.
But in the weak measurement case, you have an infinite number of possible results you have, right? And so that seems to be that the entropy calculation is qualitatively different,
That's
right? And so how does that continuous nature of the distribution enter into this calculation?
Yeah. So the first answer is that in our experiments, the continuous distribution is effectively discretized by the bandwidth of our detectors. And so in practice, we don't have an infinite number, but we turn out to have something like 30 numbers. And that increased resolution adds log base 2 of 32 is about 5 bits of it. Did off these entropy of those measurements alone to make the direct comparison between the continuous hybrid case and the two outcomes.
Isn't that cheating?
No.
Why?
Yeah, because if we wanted to make this direct comparison, what we're really trying to do is predict the outcome of our X measurement. And so what we do to get there, how much uncertainty we add by asking a continuous variable question doesn't impact that's not the question that we're comparing to when we ask the binary.
Okay, so basically your argument is because you take the difference of the information, this is some of the amount of information about the system you have latent in these continuous measurement results is the argument.
Yeah. The way to say that mathematically is that this difference in entropies is related to the independence of the two probability distributions. So if the weak measurement was independent of the other measurement, then this difference would equal the entropy of the other measurement, the strong measurement.
All right, any other questions or comments for Jonathan? All right, not hearing any. Why don't we just go ahead and thank him again? Thank you. All right, if anyone is around, you want to join us for lunch, you're very welcome. We're going to go over to the faculty Athenaeum for lunch afterwards. So thanks again, and we'll see you all next week.
Thank you, everyone.